Namaste. I am going to talk on how to use the SDSS Spectra for classroom teaching for the undergraduates. Based on my experience of over 2 decades of teaching the motivated undergraduate students in Bangalore Planetarium. This is the abstract itself, so it is available, so I don't need to read out the whole thing. Effectively, what I'm trying to say is how I use the SDSS vast collection of spectra as a tool for teaching spectral classification of stars. It served to twin purposes of estimating the temperature and identifying the spectral feature. How exactly I proceeded with this scheme, I'm going to explain in detail in the next slides. I worked at the Jawaharlal Nehru Planetarium in Bangalore, and the concept of REAP, what is called as the Research Education Advancement Program, came up here by a systematic effort to attract students towards motivating them for research in astronomy, astrophysics, or any branch of physics for that matter. So they come to us, they are doing their undergraduate courses in different colleges in Bangalore, and they spend the weekends with us, both Saturday and Sunday, whole day, trying to learn basics of astronomy, mathematical physics, and so on. That's for 1 year. In the second year, they are taught some advanced topics by the scientists from research institutes like the Indian Institute of Astrophysics, Raman Research Institute, Tata Institute of Fundamental Research, and so on. In the third year, these people will proceed to one of these institutes to spend the weekends with one of the scientists there in a small project which involves research methodology. The whole scheme is aimed at non-formal education just to motivate them to take up a career in research. This was the brainchild of Professor S. Lokanathan and Professor B.R. Iyer and also the Professor Vishweshwara, the founder director of the planetarium. We have 3 programs called the SEED, which is for very tiny kids, age group 7 to 10, let's say. Science education and early development. Then we have SO, which is for slightly more advanced students, high school students. They do they learn science by hands-on activities. And the undergraduates, and they have the research education advancement program. In the planetarium, we have about 300,000 visitors per year. Out of them, only 10% or 20% will come back to the other popularization programs we do, for example, the eclipse and so on. Out of that, another 10% only will come for educational programs, which we do, as I said, seed, sow, and reap. And only about 10% of that will come for these research-oriented programs called REAP. Effectively, we have only about 25 students per year, and out of the 100 or odd students who made it to the final year of REAP, I am having some statistics. More than 50% of them have taken up PhD programs, not only in astronomy or astrophysics, but in other branches of science also. Some of them have become very good teachers. Some of them have joined the research institutes as research assistants. We have a considerable number of them lost to the IT sector, and some are still undecided on what they want to do next. So this way, this has been a very fruitful course, and I thank the institutes who participated in this program. We also have a very small 6-inch Coude telescope, which I used for, of course, it is used for popularization programs at the occasion of eclipses, but I used it for teaching these students about spectroscopy. So when they come to us as a young undergraduate, the first year, their knowledge of spectrum is limited to the prism. Some of them would have done some experiments with the prism. They know what is a spectroscope in the laboratory. And some of them who are in the second year or so, they would know about the gratings also. So in theory they would know, but then the experiment is limited to the prisms generally. So the prisms are dispersive elements, they know. So what I have to teach them is how to convert this band of 7 colors into a graph, which we are going to define as the spectrum. So the spectrum grating spectrographs are introduced, and the small telescope that we have I use to show them the grating spectrum using the same setup which they are familiar with in their regular undergraduate courses. In the process, they understand what's the meaning of resolution, what is absorption, what is emission, because we are demonstrating them not only with the sodium light but with the sunlight also. And then I also borrow the idea of a flame test from chemistry, which we demonstrate and make them also do the experiment to identify a color associated with a particular element. Of course, they are introduced in the theory sessions about Planck's black body radiation. I don't need to spend much time on that, but I use only the formula for the purposes here. Now, after discussing all these things, I need to take them on thinking how to get the star spectrum. So effectively, I have to convert the 7 color band into a graph like this, and I have to tell them that this is the graph we call as the spectrum will be used for identifying the temperature and the other chemical elements in the spectrum. So they learn that the sunlight spectrum is like this with absorption lines, and what is the meaning of the absorption lines and how we interpret them is the procedure now. So there are 3 types of spectra, which is of course taught to them. So this is the continuum decided by basically the temperature. This is the black body curve. And then superposed on that are the absorption lines, which will tell them what is the meaning of absorption. And then when we use the sodium light and demonstrate the emission line, they understand what is the emission line also. So the characteristic feature of this, from what you see through the eyepiece of the spectroscope to what you see as a graph, they will understand by this process. So the Planck's formula now gets converted into a graph like this. So this is they are very familiar with the 2 laws associated with this. And so how it is dependent on the temperature, etc. All that has been taught. So we use only the final formula here. So I chose 2 wavelengths called at say 500 and 700 nanometers. And why I chose these 2 particular wavelengths is to be explained to them. Then what would be the ratio of the fluxes that is emitted at these wavelengths? It is solely a function of temperature. Therefore, they have to assume a temperature. So, because they know the formula, each one will pick up a particular temperature and calculate what should be the ratio of the flux at 500 and 700 and what's the ratio for to another pair of wavelengths. Now the results that are plotted by them on the board. So I prepare the board, blackboard. It's not using any Excel, and ask them to give me the numbers. And so I fix the scale on the x-axis and on the y-axis, and then each one will come and put his dot on the board, so that what starts as a random set of points finally becomes a beautiful graph. So then I tell them about the slow and digital sky survey, and they are thrilled to know that this is the way the spectra of the stars are taken, and it provides a very useful educational resource material also. However, they will not be able to grasp the entire meaning of it unless they have already done the exercise which I described till now. So the first step is to show them a sample SDSS spectrum and ask them what they were able to understand with that. I prepare it specially without any legends. I will just show one sample, and then the concepts that we are going to discuss will include what is the visible range of wavelength, what are the prominent absorption lines, and the meaning of Balmer lines and the resolution, and what is the meaning of continuum in a star spectrum. So this is the sample spectrum I show them. And as you can see here, this is having only the units on the y-axis, which is f lambda in terms of 10 to the power of minus 17 That itself is a big surprise for them, that we are able to measure fluxes of this small order. The x-axis is not indicated. We have only the coordinates of the star. But now I attract their attention to the green band below here, and what is the meaning of this? Why is it there? And why is it looking different? And what is this particular singular standing peak here and some small peaks here? How do I understand? And what are these green lines and what are the absorption lines and so on? And because they are exposed to the Balmer lines already, I tell them that this is Balmer alpha and Balmer beta, H alpha and H beta, because they know the wavelength. They can now fix the wavelength scale on the x-axis. So that is done. This takes quite some time, but ultimately they understand the meaning of the graph. Then I show the original spectrum from SDSS, which gives all the identification. So their identification of H alpha, H beta, etc., H gamma, all those things are all correct. So this is the, now we are ready for the calibration. So this is the basic formula for black body. So we choose two wavelengths. As I mentioned earlier in the spectrum here, I explained to them what's the meaning of wavelength, the continuum. So I have chosen 500 and 700, which are free of any effect of the absorption lines. So some of them would prefer to choose 600 and 800 or 750 or something. So that also is possible. So there are two pairs of calculations each one does using this formula. So as you can see, the calculation reduces to the ratio of only lambda 1 and lambda 2, and this constant, and there is no shortcut method which they will realize. They can't take logarithms and do away with it. They have to calculate this very precisely. In this step, they make a lot of mistakes and ultimately they correct themselves. So this is the graph which we get finally for two sets of wavelengths. So they notice that there is a trend, and how to use this trend for getting the temperature of the star. That is the purpose. So we go to different stars at these two wavelengths. We measure this flux ratio and read out this thing here, and we get the temperature. So the x-axis is the temperature and the y-axis is the flux ratio. So now they are able to estimate the temperature of the star using the SDSS spectrum. So now comes the discussion part. So just by looking at the absorption lines, can you tell the spectral type? Well, temperature we have estimated, but just by looking at it, because for some of them the absorption lines are very strong, and in some cases the absorptions of other elements are very strong. This is discussed. And the overall shape of the curve itself will give you an idea of the approximate estimate of the temperature. And of course, they identify the Balmer lines very easily by now, and the predominance in the B and A spectral types. And the y-axis values also, some of them have a scale ranging from 1 to 5, some of them from 10 to 20. So it is related to the brightness of the star, and therefore the errors are smaller, and therefore the exposure time also will be less. And that green band has something to do with the city lights, and therefore the moment I tell them that it is because of the mercury lamps that are used for street lighting, the next question, what if a star has mercury in it? Of course, there are chemically peculiar stars with excess abundance of Hg. But that information will be lost because of the city lights. So we have to think of a mechanism wherein we suppress this, go to a dark side, and so the related discussion takes place. And now I introduce them to the SDSS website and ask them to download as many spectra as possible and estimate the temperatures of many stars. Now, the RA deck, they are not able to connect to any particular star because the brightness information is not available. Well, they are over enthusiastic, so they download so many spectra from that, and invariably there will be one student who will download a galaxy spectrum. I'll show some examples. So these are the four stars So just by looking at the shape of the curve, they are able to tell the temperature. They have identified the flux, the Balmer lines. They have also measured the flux ratio, so they have estimated the temperature. When I give them hard copies like this, they on the reverse side they give all this information, and that is saved, not digitally, but hard copies are saved. And then comes the galaxy spectrum, which looks somewhat similar to a late type star spectrum. But then I attract their attention towards the identification of H alpha, which is not at 6563 angstroms anymore. It has shifted. So this tells them that how to distinguish between the spectrum of a star and that of a galaxy. And further, after the sessions on stars are over, I introduce them to the galaxies, very basics also, the overall shape, what decides the overall shape, and also the shift of H alpha as a measure of the redshift. So they are introduced to the meaning of redshift also in case of this. So here in the lower part of the spectrum, they will see the word galaxy plus the meaning of Z. This is the redshift. This is indicated. So these are several examples of the galaxy spectrum also, which are borrowed from the SDSS. So now we decide to make a library of spectra. So many stars have been studied, and then they are now enthusiastic to go do this experiment themselves, go to the telescope. So how do we prepare the list of stars? We have to start with the calculation of the sidereal time at sunset on the range of right ascension of stars that are available through the night, and then because we have only one night at our disposal, we have to collect as many samples of all spectral types. So we go in batches of 6 or 7 students. Each student will have prepared 6 to 7 stars of different spectral types, and I ask them to choose the bright ones so that the time needed for exposure or the atmospheric correction is reduced. Then they estimate the temperatures and compare with the spectral types. So this is the observatory, which is very close to Bangalore, operated by the Indian Institute of Astrophysics. This is the 40-inch with the spectrograph attached here. And so these are the students who spent the night. So we go in batches of 6 to 7 of them. And one occasion, it was an eclipse, lunar eclipse day, so we were able to get the spectrum of the moon also. This was studied by another senior student with great enthusiasm. The blue lines correspond to the spectra of the slit position on the eclipsed moon. So these are the types of experiments we did there. So we were able to carry out this and motivate the students towards understanding the spectrum of stars, how one goes about taking it up. So I expressed my gratitude to the directors of IIA, Raman Institute, and all the others who are, very actively participated in contributed to the success of this program. And the faculty from the Indian Institute of Astrophysics who organized these trips for the students at the 1-meter telescope. And there were several PhD students who taught IRAF to these students who demonstrated and obtained the spectra free of atmospheric correction. And finally, the staff of the observatory who were very cooperative. So this is what I want to share, and I hope I have conveyed my humble efforts to you. So this is not something not doable. So I am happy that Shaw-IAU organizers gave me this opportunity to present this. Namaste. Thank you.